The Palomar Transient Factory's team of astronomers, which includes Carnegie's Mansi Kasliwal, has observed the early stages of a Type 1a supernova that is only 21 million light-years away from Earth. It is the closest of its kind discovered in 25 years. The supernova, named SN2011FE, was discovered just 11 hours after it exploded in the Pinwheel Galaxy on August 23rd at about 4:30 p.m. Universal Time. The team's detection of a supernova less than half a day after it exploded will refine and challenge our understanding of these stellar phenomena. For several years, Kasliwal has been taking images of the Pinwheel Galaxy every night she possibly could using robotic telescopes at Palomar Observatory. Type 1a supernovas are violent stellar explosions. Observations of their brightness are used to determine distances in the universe and have shown scientists that the universe is expanding at an accelerating rate. In fact, the Nobel Prize in Physics was awarded December 10, 2011, to 3 astronomers for their discovery of the accelerating expansion of the universe through observations of distant supernovas. The widely accepted theory is that Type 1a supernovas are thermonuclear explosions of a white dwarf star that's part of a binary system, 2 stars that are physically close and orbit around a common center of mass. There are 2 different models for how Type 1a supernovas are created from this type of binary system. In the so-called double degenerate model, the orbit between 2 white dwarf stars shrinks until the lighter star's path is disrupted, and it moves close enough for some of its matter to be absorbed into the primary white dwarf and initiate an explosion. In the so-called single degenerate model, the white dwarf slowly accretes mass from a different non-white dwarf type of star until it reaches an ignition point. There are 3 potential methods for the transfer of mass. Depending on which one is used, the second star is likely to be a red giant, a helium star, or a so-called subgiant or main sequence star. A closely related paper in the same journal issue cited observations of the early stages of the supernova that showed direct evidence that the primary star was a type of white dwarf called a carbon-oxygen white dwarf. Another related paper, published in the Astrophysical Review, includes very sensitive and early radio and X-ray observations that show no evidence of interaction with surrounding material. Combining this data with an analysis of historical images, the team ruled out luminous red giants and the vast majority of helium stars for the second star in the binary system before the explosion. These clues meant that the secondary star was either another white dwarf, as in the double degenerate model, or a subgiant or main sequence star, as created by one of the 3 single degenerate model methods. Analysis of the matter ejected by the supernova's explosion suggests that the second star is less likely to be another white dwarf. Thus, the solution to the mystery of SN2011FE's origin is probably a primary white dwarf accreting matter from a neighboring subgiant or main sequence star. Their breakthrough observations were published December 15, 2011 in Nature. The Carnegie Institution has had over 100 years of extraordinary discoveries. To continue this tradition, Carnegie scientists need your support. For more information about this and other cool science, visit our website at carnegiescience.edu. This is John Strom.